Welcome to Naked Reflections, brought to you from the Wolf Institute. I'm Ed Kessler, and each week I'll be taking an in-depth look at the stories reported by our friends over at the Naked Scientists. What does the latest scientific stuff mean for the rest of us? Stay with us and find out. A 50-year-old problem solved. One of the most significant scientific results in my lifetime. What took decades of research can now be achieved in half an hour. Such were the plaudits heaped on the AlphaFold program developed by DeepMind, which uses AI to determine and predict the 3D structures made by proteins. Scientists have been researching in this area for decades, but this new development transforms everything at a stroke. The implications for medicine and drug production are profound. Claims for this game-changing breakthrough in biological science were made at the end of last year, but were they true? There's a fractious history of science journalists getting things wrong, and of scientists themselves talking up their work to get funding. Not only scientists, to be honest. Here's Stephen Curry of Imperial College London addressing this subject on the Naked Scientist podcast, Scrutinizing Science.
Most scientists rely on public funding of one form or another, and to me, that brings with it the responsibility to give a good account, in both senses of the word, of what we do with it. Some of my colleagues are more wary of talking to journalists, moaning privately of their tendency to sensationalize, but the only effective counter to that is talking to them. I've had my own run-ins, to be sure. I've taken a number of journalists to task on my blog for over-egging a story or for not taking enough trouble to get the facts straight. We've all seen the articles on miracle cures for cancer, or MS, or whatever. But it's not always the journalists to blame. A study from the British Medical Journal found that press releases in health-related research were the primary source of inaccuracies.
Stephen Curry on that exemplar of responsible science journalism on the Naked Scientists. As a theologian, I can't really make a well-informed judgment about whether the claims made for AlphaFold stand up, but I know a couple of people who can. They are Dr. Alex Taylor from the School of Clinical Medicine in Cambridge, whose Twitter handle is impressively named Antibody Boy, and Dr. Beth Singler, Junior Research Fellow at Homerton College, Cambridge, who specialises in AI. Well, taking my cue from our clip, can I ask you both, was this story hyped up? Let's start with the immunologist and synthetic biologist, Alex.
Well, it's certainly ruffled a lot of feathers amongst structural biologists. It's certainly striking how well this program has performed in this structural biology competition. CASP, Critical Assessment of Structure Prediction. So this is an academically run competition where scientists, they are given the challenge in a number of different sort of categories, if you like, to try to take a sequence of a protein. So proteins are a string of amino acids, and they're given the sequence of those amino acids, and then use that without any information about what these things look like in 3D to try to computationally crack the structure of these molecules. These are molecules of known structure, but the structure is initially hidden from both the organizers of the competition and the entrants. And then afterwards, they sort of lift the lid and have a look to see how close the structure they were able to get. It's certainly remarkable how much this seems to have outperformed its sort of rival academic groups. But we have to sort of look a little bit closer at what exactly this competition involves, and sort of there's a little bit more of the sort of devil in the detail there. I wouldn't say it's hyped up. It's, as I say, it's certainly a very interesting result that these guys have got, and it's a nice step in the right direction. But it certainly isn't the end of the road for structural biology quite yet.
Sounds like a cautious welcome. What's your view, Beth?
I would take a similar stance, actually, not to bring any controversy between your two speakers here, that coming at this from more the AI angle, again, a few feathers ruffled, but also questions about methods. There was a lack of transparency in some of the presentations about how this worked at this particular conference. There are issues around how much computation power was involved. There are questions about, does this only really apply to very specific limited data sets, whether this could be applicable anywhere else? There's a lot that needed unpacking from the kind of big trumpeting of this is the solution to a long-standing problem.
Let's take a step back. What is AlphaFold for those listeners who have no idea what we're talking about?
Obviously, from the name, it's similar in some ways to AlphaGo that people might have come across previously that succeeded so significantly, it seemed at the time, against Lee Sedol, that it is, again, an iterative learning artificial neural net system based on the deep learning technique. So layers and layers of algorithms interacting with each other in a way that is arguably similar to the neural patterns of the human brain. There's a lot of discussion about the differences as well. It took a data set of about 170,000 known structures, and it predicted what kind of correlations between the initial stage and the folded stage could be found. So we're looking at roughly a predictive ability of about 90%, which was higher than anything that had come previously. But it was dependent, like AlphaGo, on this huge number of computations.
Okay, well, let's get back to biological basics. What is the purpose, Alex, of visualizing the structure of proteins in the way this program and its predecessors do?
In biology, essentially everything reduces to kind of complex chemistry in a way. The structures of molecules like proteins, essentially how they work, right? There's an intimate connection between their shape and how they function. So really, if you want to have a sort of deeper understanding of a biological system, you need to know what it looks like at the sort of 3D atomic level. I've sort of overheard some of my colleagues from my old lab, the LMB, sort of facetiously remark over coffee that sometimes a structure is really just the kind of icing on a cake, and that you can get a lot of insights just from old-fashioned biochemistry methods. But really, in a way, seeing is believing, and it's always a real plus. And often the insights, you get some unexpected insights from then seeing like what these things actually look like in 3D. And obviously, we don't have microscopes that are powerful enough to show you that. So you have to sort of deduce it from various sort of data.
And Beth, as an anthropologist, what's been the wider reaction beyond the scientific community? Is there a fear of this? Is this sort of demonstrating the sort of apocalyptic domination of science, or what?
I don't think the volume of response is as great from my anecdotal experience of watching the conversation online. It's not quite as great as it was for AlphaGo. Setting an AI against directly a human has more impact. There's a greater history of games against AI, like with Deep Blue. But there still were those apocalyptic responses. I saw a few people online suggesting that the next stage after this would be AI in charge of creating their own proteins, creating their own physical forms, taking over the world. These narratives drawn from science fiction pop up again and again.
Maybe we should give them a chance. They might come up with a better world.
I mean, that's also an argument. My work looks at both existential fear and existential hope. So for some people, this is a hopeful path that perhaps AI could do a better job with our biology than we've been doing. But perhaps because the subject itself, the biological subject, is quite complex, the general public didn't necessarily grasp what AlphaFold had done in the same way, grasping what AlphaGo could do, or even, the games that can play, the AI that can play games like StarCraft is a little bit more visual and obvious to the general public.
You joke, Alex, but is there some truth in what you said?
Beth just touched on there. Often there is this public knee-jerk negative reaction to these sorts of terms, AI and neural nets and so on being kicked around. And if you look in sci-fi, you don't have to look very hard to find sort of mostly negative examples of these things. The application of these tools can be manifold, and some of these things can be optimizing things that are good for us. Let's just crudely say you probably would do very well to put an AI in charge of, say, traffic planning. So if you want to have something where an output that maximizes, say, human positive experience in some way, using some resource in the optimal fashion, an AI might be far better at this than a human planner. And yet the output is, a reduction in human misery, if you like. Although on the other hand, humans, we've got a good track record of using tools for negative stuff.
I wonder if we could discuss what impact this might have on medicine and drugs.
Being able to predict sort of a wider range of protein structures and how drugs might interact with these, it might allow us to sort of design or screen a greater variety of drugs against sort of molecules involved in medicine.
Let's just explore whether actually we're making much more of it than is necessary. I mean, is it simply that we're speeding things up, or is there actually a breakthrough in our knowledge of proteins?
There is a little bit of a criticism of the sort of opacity, in the sense that, it being Google, we don't get to look under the hood yet. And I think there is a promise that they will publish some work on this, but the coding, they are not going to make this available. And I presume the plan is to monetize this in some way. As far as I understand it, their approaches are somewhat novel, but they're not so revolutionary that many of the ideas that they're using and implementing in their software have not been kicked around in the field already. And perhaps, you can argue that they're using this sort of huge resources of this multi-billion-dollar company to sort of crack a nut that is much more challenging for academic groups. But without a doubt, the results are impressive.
It does raise that interesting question of the ethics behind it, Beth. And I know this is an area of interest of yours. Google is a private company and it's not renowned for sharing everything. Do we have an issue here? Is this something we should be worried about?
There's several facets to that. I mean, Google's come under criticism before for, again, as you say, hyping up AI products that it's trying to sell. And in some cases, we've then dug around and say with Google Duplex, one of their AI assistants, they were very happy about trumpeting, found out quite how many humans were involved behind the scenes to make it seem like the AI was better than it was. With DeepMind, they are slightly different beasts in that it's less corporate. It's hugely, hugely funded by Google. So there is no concern in the way there are in academic institutions for the constant rinse and repeat of academic funding searching. The people there have their own kind of community and culture without the precarity that most academic scientific researchers have. So we're seeing sort of the ethical issues around how we actually do science, as well as what the science leads to, which is perhaps more Alex's domain in terms of the biology. The other competitors just don't have the access to Google's resources. So this kind of limits and puts a halt to collaborations. Again, as I said, the methods were not very transparent. We don't entirely know how these deductions were come to. And there's a sense in some of the conversation of AI researchers suggesting this is more of a workaround than a solution. It doesn't necessarily add anything to our understanding of protein folding, but actually just sort of gets to something that's a good enough guess. At 90% accuracy, that's something some people were predicting would take another 10 years to get to with machine learning. So it is a leap forward. The question is perhaps, is this a leap in the right direction in the right way?
I think this is a bit of a reflection of something that we've been seeing in science for decades now, which is just a steady encroachment of proprietary processes, technologies presented to academics as a service, but essentially you don't get to see what's under the hood. In my own work, I regularly use deep sequencing, so that's sequencing millions of strands of DNA. And many of the instrument providers don't want you opening up their machines and having a look at what's going on. And the kits that they provide for doing this sort of work, you get a series of colorless liquids and you don't know what they are, essentially. I mean, you can dive back into patents and older papers in some cases, but many of these companies don't publish their sort of newest bits of work. So essentially, you're sort of working a little bit in the dark in some ways. In large part, this is, in a sense, a reflection of how complex biology is. Your average researcher can't afford to take the time to become an expert in sequencing and bioinformatics and analyzing mass spec data. You just you're addressing a biological problem often, and you just want to know, what's the sequence of this? What is the mass of that? You haven't got time to become an expert in a dozen different fields. And companies have sprung up to be able to sort of respond to that need in a way.
It sounds like the ship has sailed in that sense, that it's too far gone.
In most cases, there is this pressure always on to get your research done as quickly as possible because money is always running out and we need to apply for grants, we need to get papers out, people need to get their PhD theses submitted. So it's always about getting stuff done quickly. And hopefully we try and do it with high quality as well as rapidly. But of course, you need to turn to kits and off-the-shelf reagents that a company has prepared for you. And in a way, this is exactly sort of large companies like Google stepping in to allow you to do this sort of software work is another aspect of that.
You're listening to Naked Reflections with me, Ed Kessler, and my guests this week are Alex Taylor and Beth Singler. And we're discussing what's been called biology's Holy Grail, a recent breakthrough in predicting protein structures. Research into this area started in the 1950s. Here's Megan McGregor speaking on the fascinating Naked Scientist podcast, Rosalind Franklin, The Hidden Story of DNA. The clue is in the title.
Rosalind Franklin used X-ray crystallography to create Photo 51, a black and white picture showing an X shape made up of spaced apart black splotches. And it was thanks to this photograph that the structure of DNA as a helix was figured out.
Can we look back at the history of this sort of research, which started with X-ray crystallography?
Crystallography was the real beginnings of getting to see what some of these molecules could look like at the atomic level. I actually did my PhD in the department where Rosalind Franklin worked at King's College in London. I remember once, actually, in the middle of my PhD, somebody discovered a handful of her notebooks hidden in some old drawers somewhere. So again, these things are models, but they're models informed by data of what the 3D structure of a molecule looks like. And in getting this sort of information, you sort of really get to see some clues as to how it might function. But even you asked me earlier on about drug discovery. One of Britain's other great X-ray crystallographers was Dorothy Hodgkin, who worked in Oxford. She was the first to sort of solve the structure of penicillin. And by having that structure, you immediately had sort of some clues of how to chemically modify the penicillin structure to be more stable. I mean, in the early days of penicillin, one of the big drawbacks was that it would break down very easily. And so through this sort of deeper understanding of the chemical structure of penicillin, chemists could then come in, make modifications, and make the sort of the more stable forms of penicillin that we still use today.
So I just wanted to ask a very quick question, which maybe doesn't have an immediate answer. So AlphaFold is dealing in simulations. Is that significantly different to seeing a visualization of the structure of DNA versus simulating it in a computer scenario? I mean, I'm not a crystallographer, but that's a different process. Does that make a difference to how we have a scientific discovery?
Even with X-ray crystallography, and even to an extent cryo-EM, a companion or some say a sort of successor technique in structural biology, you're still making a model, which is essentially a simulation to explain the data that you've got from these experiments. Essentially atoms are too small to see directly. So you're always sort of indirectly measuring these structures and then making a model that fits that data. And of course, then scientists refer to this as truly seeing it.
Beth, what lay behind the question there?
Oh, it's general conversations that happen online about the difference between simulation and knowing and how we use language around AI. So we'll say the AI learns or the AI knows or the AI is seeing, and whether there are lines of distinction there that obviously with crystallography, you're not directly seeing, but is that different in the same way as a simulation is different from seeing? So I'm just curious about whether the way in which scientific method was inspired by seeing the structure of DNA would be different if we're not seeing it in the same way. I'm using quotation marks over seeing because there's obviously these different varieties of ways of seeing.
Can I unpack that a bit more? Because it might feed into what Alex is talking about, because the language is so important, and just the very word to see, right? And Alex is saying, well, it's too small to see anyway. So what are we seeing? We're seeing something indirectly. And then you've got the language of reveal, right? And then it goes into this sort of foresight and perception and all these different terms that we use in everyday speech. And we've got to be very careful about the language that we use. And Alex has been very careful with the language that he's using. But just help us a little bit, Beth, in terms of the language of talking about AI. And I just wonder whether that sheds any light on the description that Alex has been giving us.
It's very easy in public discourse around AI to fall into language, as you say, that replicates human modes of doing things. So things around agency, actions, seeing, doing, understanding, learning. These are all words used about AI, but it does not happen in the same way it happens in humans. But there's the argument about to what extent AI is moving towards doing things in similar ways to humans. We're all naturally, myself as much as anyone else, limited by our existing cultural context and the words we look for when we try and describe something that is beyond our current conception. So that, as I was saying earlier, I think the discussion around AlphaFold has been much, much smaller than the conversation about AlphaGo, because AlphaGo fit more neatly into this competitive AI versus human scenario. Go itself had a whole history of language around divine moves and a history and development that kind of set up the scene for what was happening, for the story we wanted to tell. And this was very apparent in the press at the time. And we see some of this in the press around AlphaFold. So there's the way it's been described as a holy grail of biology, which, instantly my little antennas go boop, 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 because I find the use of religious terminology in particular in AI discourse. Very, very interesting. But I think with terms like Holy Grail or quantum leap or all the other hyped up terms that are coming out, it comes with the cultural baggage as well. Holy Grail, from my perspective, in the pop culture discussion around the Holy Grail rather than the more spiritual religious discussion, it can be emblematic of a fool's quest. So for the Arthurian legends, for me in particular, Indiana Jones and the Last Crusade, my son's named after Indiana Jones, this idea of having something that's so all-consuming, it can lead to perishing. So at the very end of Last Crusade, spoilers for people who still haven't got around to seeing a very old film, there's this focus on getting the item, and the Nazis fail because they are so focused, whereas Indiana Jones makes a decision not to. So there's this whole subtextual communication going on when the press, the media, and individuals start hyping up AI in these particular directions. And we need to pay attention to whether that has an impact on the conversation in the direction the science and technology is going in as well.
Well, God forbid that naked reflection should hype up the context. But Alex, does the question of language and the choice of words, does that impact on what you do? Or are you're there with your test tubes and your tools and just getting on with it?
No, I mean, I think certainly the sort of interpretation of work is all important. Yeah. Having published some work in sort of origins of life field, people sort of then hanging all kinds of connotations on this, that was one of the many things that you have to deal with as a scientist in that field. There's a danger in being too vague where you sort of say, the holy grail of biology. And I think one thing that I noticed is there were several ideas kind of being conflated around all that. In this area anyway, the true holy grail would be, if I say I want an enzyme, let's say, so I want a molecule, often a protein molecule, that speeds up a particular chemical reaction, can you sit down and type me out the sequence of the protein that does that? And let me be clear about it, we're absolutely nowhere near that, nowhere near. So most of this sort of folding prediction is based on things where we have some frame of reference for it. And in my view, anyway, the real holy grail would be being able to say, well, here is a process I want to be able to catalyze. It could be something like, I want to be able to fix more CO2, or I want to be able to make a thing that will break down a toxin, let's say. How do we design a protein to be able to do that? And that is a whole field of itself. One of the sort of rival academic groups of AlphaFolds is a group of this guy called David Baker in Seattle, who's sort of led the field academically for many years. Despite decades of work on this, they're getting better at it, but they're still only able to do this for very, very short proteins. And anything as sort of the size of a typical enzyme that we find in nature, it's not possible currently.
We're coming towards the end, and I suppose I have to ask, do you feel fearful or optimistic? I guess the simple answer is you feel both. What are the next steps?
Well, I think they've clearly shown that sort of taking their approach is a good one, and they've managed to sort of make a good step forward. I suspect the next steps in that field anyway will be for academics to try and, in a way, recapitulate that bit of work. But by and large, structural biologists will keep doing what structural biologists do. I think hopefully we will see more and more academic work informed by these sort of software. But as I said earlier on, they're certainly not out of a job yet.
Beth?
Yeah, so I think what's fascinating about DeepMind in particular is the way they almost seem to have, at least looking from the outside, a list of big problems that they think AI and deep learning in particular can sort, and they're almost sort of ticking them off one by one. And it's still unclear, and perhaps it's also unclear to Google to a certain extent, how this rolls out beyond these big splashes of pedals into the pond and all the reverberations that have the impact on the discourse. But it's still very much the experimental phase, and Google, as we said, has put billions and billions of dollars into DeepMind that has to start at some point ringing back out. And if the stated aim of DeepMind, as they have on their website, is to solve the problem of intelligence, and this is the path that they're taking, there's still going to have to be a step in between where Google sees some sort of return on all these small pebbles into the pond and the big problems that DeepMind's been focused on. So I absolutely think in the next year or so we'll have another big announcement about another super long-standing scientific or technological problem that DeepMind has solved in some way. But it's whether that just continues until Google sort of calls ends on it and says you're not actually getting to intelligence like we wanted you to.
Well, there we are. I'd like to thank my guests, Alex Taylor and Beth Singler, for sharing their expertise with us, and I'd like to thank you for listening. We'd love to hear from you at nakedreflections@wolf.cam.ac.uk. We'd like to know what you think of the show, and if you want to hear more of our groundbreaking podcasts, you can catch up with our back catalogue. There are episodes on conflict resolution, grief, the American election, and many, many others. You can subscribe to the Naked Reflections podcast wherever you access your podcasts or at nakedscientists.com/reflections. I'll be back next week with some more guests.